Welcome, and guys, please feel free to tap in at any stage if you feel like I haven't described things as clearly or well as they could be, because I'm sure you have your own opinions on how this stuff works. So I thought, as a nice way to sort of get started with how to use Status itself and how to build DApps, that this would be a good dry run to see how we can put together useful and entertaining educational content by going over some of the amazing resources that are put out for free in this open source ecosystem. So there's a great bunch of people, mostly based in South America, called Zeppelin Solutions, and they build audited libraries of smart contracts that sort of cover all of the basic patterns that you need in Solidity. This means sort of basic ownership patterns, crowd sale patterns, token patterns, everything that you want. So if you want to check out their GitHub, just go to GitHub and search for Zeppelin Solutions. That also, one of the cool things that you can do is use this Brave browser. Sorry, not Zeppelin's. Open Zeppelin. And Brave comes preloaded with MetaMask, which is what we're going to be using for this particular tutorial. If you want to chat about some of the downsides of MetaMask, then Ricardo and Richard are really great to talk to because there are some downsides, but we'll get to those as we go through. I'll send out the Open Zeppelin link in the meeting notes for this. Sorry, I'm just not logged into my GitHub for this presentation. So they've put together a series of 8 different situations with smart contracts that you can go through in order to learn more about the vulnerabilities inherent in some of the things that have been written. So all of these contracts come from different ways that smart contracts on Ethereum have been hacked over the last 2.5 years. So it's a really instructive sort of set of tasks to get you into thinking about how to write properly secure smart contracts. All of these are written in a language called Solidity, which is currently the most popular language to write smart contracts in Ethereum. As you would have seen from Jacques' presentation in Bangkok, there are other alternatives to this. He's working on Viper, which is a Python-like language, and then there's something called LLL, which was the low-level language or the lovely little language, depending on your interpretation of it. But Solidity is the most popular. It looks fairly similar to JavaScript. I think the easiest way to imagine it is sort of as strongly typed JavaScript with object orientation sort of baked into it. So you can apply the notion of inheritance to your contracts, which is something that we'll get into in the course of our tutorials. If you want to take a look at the sort of latest Solidity docs, they're really good. They go into much more detail than I will over the next sort of 45 minutes, and are a really great place to start if you want to dive deep into understanding both the strengths and some of the limitations that come with Solidity. A lot of which, in terms of the limitations, are sort of highlighted in these tutorials, which is sort of the point. So if you want to follow along, which I sort of strongly suggest because it's quite fun, essentially what we're gonna be doing is all of the games that happen around each of these smart contracts get played in your developer console. So unfortunately, Brave doesn't sort of include the developer console in the window, but if you hit Command-Alt-I on your Mac, or if you're on Windows, I think it's Command-Shift-C or I, or Control-Shift-C and I, to get your developer tools up and go into your console, you'll see a whole bunch of information printed in pretty psychedelic colors, which is quite a neat way to sort of play the game. And we're going to go through each of these ones, perhaps not re-entrancy and elevator, but just the first 6, to give you guys a sense of both how Solidity works, how smart contracts work in general, and how they can be manipulated just so that you're aware of sort of how best to write defensive patterns when you're thinking about this stuff. The first thing that you'll need before we really begin is MetaMask if you haven't got it already. Essentially, you can imagine it like a wallet for your browser, but it's probably better to describe it as a keyring. It's where you store all of your different accounts and can interact sort of directly with dApps from your browser. There are several limitations to doing this, and we sort of don't recommend keeping any Ether in MetaMask because it's not necessarily the most secure way of storing your Ether, and also it injects a whole bunch of information into every web page that you visit, which can be sort of used against you for advertising purposes, which is not so cool. But it's useful for this particular tutorial. The other thing that you'll need to do if you are following along is go to faucet.metamask.io, and this is where you can sort of get some test Ether for Ropsten, which is the test network that we're going to be working on. So you can see down here, you've got a sort of drop down that you can choose which network you want to join. We're going to be working on Ropsten, which is the closest sort of mimic of the main Ethereum network in the sense that it runs the same consensus algorithms as Ethereum itself does, i.e. proof of work, whereas the other ones, Rinkeby and Coven, run something called proof of authority, just because Ropsten has been attacked so many times because the Ether on it is worth nothing. So it's very, very easy to sort of spam the network, which incidentally is like a really great explanation in the real world for why crypto economics is actually a real and important thing. The fact that Ropsten and Morden before it have been killed by people sort of spamming the network with useless transactions is indicative of what happens if you don't have any value behind your native token. Anyway, the other place that I wanted to show you just before we actually dive into the code is like if you really want to go and like if you know nothing about Solidity, then Ethernauts is quite an advanced place to start. And so if you really want to learn from like the very bottom, cryptozombies.io is really the place to go. They have some really, really awesome tutorials. It's very, very interactive. You get to build your own zombies. They eat crypto kitties. It's huge amounts of fun, and it certainly starts at a lower level if you've never really like seen much code before in general. Then perhaps Crypto Zombies is the place for you. But most of the guys on this call, I think, are developers. So we're going to dive into Ethernauts, which is quite a bit more fun, if you ask me, from just a technical challenge perspective. So what Ethernauts does, if you sort of read through the sort of short abstract here, is that it has a contract called Ethernaut running on the Ropsten network. You don't sort of interact directly with that, but you deploy your own instances of each level, and then you sort of hack them or otherwise manipulate them in order to learn something new about how Solidity works and doesn't work sometimes. So essentially what they do is they deploy this contract onto Ropsten, they wrap it in what we call an application binary interface, which gives you access to all of the different methods on this contract, and then you can call that directly through your developer console. And when, guys like Gavin Woods say, Ethereum is this global computer that all you need is a JavaScript WebSocket to interact with and program on, and that this brings like a completely new paradigm shift into how we think about consensus and, sort of connection with each other. This is exactly what he's talking about, right? We're going to use like our JavaScript console as you ordinarily would for web development and talk to actual smart contracts that run on this global computational substrate that everybody agrees upon, which is kind of awesome. So we can check out the Ethernauts owner if you sort of type it in here, and you might find if you're working with Chrome 62 and above that you have to use the await syntax to handle the promises. And there you get an address returned, which will sort of like tell you who the owner of that Ethernaut contract is, which is OpenZeppelin. And then what we want to do is start inspecting the contracts, work our way through the information that's stored in it, and see if we can complete the first level, which is Hello Ethernaut. So the first thing that we're going to need to do is get a new instance. And if you do that, you'll see that it pops up a transaction in MetaMask for you to sign with your accounts. I'm going to submit that onto the network. It should pick that up in the console here. You can see that it's sent a transaction. And this is also really useful because, I think that a lot of the other ways of learning Solidity don't actually interact directly with live networks. So you can actually see the delay as the contracts get deployed and get a better sense of what it's actually like to develop for real on Ethereum. So we've deployed our contracts. We've got the instance address back. And now it's sort of time to start interacting with it to see what we can do to get out of it. And they give us the first thing that we should call on the contract in order to get started trying to understand what's in this contract and what we need to do with it in order to complete the level. So if we wait the contracts .info, and essentially what we're calling here, like in .info, right, is just a public variable that's been declared, and clearly in this case a string. And what it returns to us is you'll find what you need in info1, right, which is clearly another function that we need to call. That's made available by the smart contract. So when you declare public variables in Solidity, it's pretty neat. It goes and sort of makes automatic getter methods for you, which is why we can just directly call info or info1 in this case. So if we go ahead and call info1, see that we now need to try info2, but we need to pass in hello, the string, as a parameter. So if we do that, see that's the next sort of, so we're just going to go through these instructions and practice. Essentially what we're doing here is just getting used to the idea that you can call methods on a smart contract directly from your JavaScript console, right? And then this translates obviously very easy into writing, the sort of basic JavaScript based distributed applications that will live within Status. So when developers are working with our API and Status Dev CLI, which is sort of the SDK, this is the kind of thing that they will be doing, but obviously from JavaScript, not directly from the console. It's just really, really cool that I can interact with like a world computer from where I'm sitting. So let's take a look at InfoNum. You can see that this is an array, and essentially there's the number 42 being stored in it. So there's something about 42 that we need to try and understand. And if you take a look, obviously we've got sort of really neat autocomplete here in our terminal, and there's a method on this contract, or a method being returned by the ABI. That's allowing us to interact with it, that is info42. So why don't we give that a call? And you'll see that's it's just leading us through everything that happens in this contract. So let's take a look at the method name. And then there's this method. So again, we'll just carry on doing this. Method. So we haven't yet found out what the password is. So it's clear that we can't sort of call authenticate just right yet. So if we look on the contract object again, it turns out that there is in fact a password object as well. So we can get that. There's the password, and now the last thing that we need to do in order to authenticate with our smart contract submitted and move on to the actual sort of trying to hack the contracts part of this tutorial, we need to sort of pass Ethernaut 0 in as the string to the authenticate route, right? So authenticate 0, and it should sort of pop up again a transaction in MetaMask. Because in this case, so this is quite an important point to note as to like why it never asked us for to sign any transactions when we were calling this information, but as soon as we called authenticate, we needed to sign a transaction from MetaMask, and this is because any read, when you call data from Ethereum, that is for free, right? So it's only writing to the network that actually costs gas and therefore has a cost associated with it in Ether, and is the reason that you sort of need to sign off on that from your accounts. So Authenticate is clearly changing the state of Ethereum, and therefore we need to pay gas in order to cover those sort of state-changing computational steps. Whereas when we were calling this informational stuff that was leading us through the contracts in a fairly heavy-handed way, all we were doing was reading data from the state. We're not manipulating it, therefore we don't need to pay any fees. Our transaction has gone through. We should be able to submit this instance. Again, it pops up a transaction in MetaMask. Submitting your instance back to the main Ethernaut contract is sort of how you advance through each level. So this whole CTF is played through that Ethernaut contract, and it sort of shows you just how sort of easily interoperable and how fun these kind of networks can be to build on, right? Because everybody is using the same contracts, and there was, in fact, when they released this around DevCon 3, there was this big race between a number of people to try and solve it first, because there was a reward associated with that, which is something that I think we ourselves can learn from at Status in terms of thinking about how we can best educate people and keep them coming back to learn more about Status in particular. So we're just waiting for this transaction to be mined. And again, it's pretty neat, I suppose, that you actually get a better sense of just how slow sometimes these computers can be, and how far there is to go in terms of the developments and sort of maturity of these technologies. There's obviously some really, really fun and exciting scaling stuff that's happening at the moment, and I recommend that you go and check out the ETHCC videos from last week, which were happening while we were in Bangkok, and there's some really, really interesting scaling talks there. And you can see, while I've sort of been waffling on about that we've submitted the instance to the Ethernaut contract. It's checked it agrees that we've gone through the whole thing and authenticated ourselves with the correct password. We've completed the level, and we can head on to the next one, which is called Fallback. Before we go there, are there any questions? No. Go. Cool. So Fallback has to do with sort of what's going on in the actual Solidity contracts, and this is the first time that we get to look at sort of what Solidity actually looks like. And it's not the greatest contract, I suppose, to introduce you to, but if you've seen JavaScript before, then a lot of this should sort of make sense. What's going on in this file is at the very top, what we need to do is sort of declare our compiler version of Solidity, and we do that with some syntactical sugar called pragma, and then we just specify the version. At the moment, I think the latest version is 0420, but we're still working with 0418 here, which is very chilled. Like the versions come out fairly regularly, especially minor versions. And then you sort of have access to import other contracts into your own contract, which is what I was talking about in terms of imagining Solidity as it's sort of like TypeScript, right? Strongly typed JavaScript, but it has this notion of inheritance with it, right? So if you imagine a contract as an object, then it can inherit properties from another object. In this case, we've written a contract called Fallback, and this Fallback contract is ownable, which is one of the contracts that comes from these Zeppelin Solidity libraries that provides like a safe pattern for ownership of contracts. And this means that whoever sort of deploys this Fallback contract will be the owner, right? So you can see this is the other thing that's very similar to object-oriented environments is that if you name a function in your contracts after the name of the contract, it becomes the constructor, and it gets called once at deploy, and that's sort of what will set, for instance, in this case, it will set the mapping contributions of the person who sent the message to 1,000 Ether, right? There's quite a nice sort of Solidity cheat sheet that I want to show you, and that I'll also pass around once this call is done, which gives you direct sort of access and explanations of all of the global variables that are available in Solidity. So this is the one that you just saw, message.sender. It's a much safer pattern, right, than obviously like passing in the address of the person as a parameter. And this is one of the unique things about Ethereum, right, is you have this like completely object-oriented environment where you know always the provenance of where messages come from, right? So in the case of this contract that we were just looking at, the message sender is the person who sends the message that deploys the contract. And you always, like I say, know, I don't know of any other computing environments where you always, without a shadow of a doubt, know where a message comes from. And it allows for some really interesting sort of features around computing. There's a wonderful video from Gav Wood from very early on, I think DevCon 1 or DevCon 2 in London, that goes into detail around the ideas that goes into detail about why provenance was such an interesting feature to have in Ethereum. And again, like I'll share that video after this talk is done. So, like I say, if you want to learn more about Solidity, like Crypto Zombies is the place to go. But here, what we want to try and do is claim ownership of the contract and reduce its balance to zero, right? So this is where like the fun really begins. We get to like actually think about like how do we hack this contract, right? So we've set it up. We've said that it's ownable. It should be like this ownable contract is audited. It should be fine to work with. And yet there's something in this contract that will allow us to take ownership of it maliciously and then drain its balance. So let's get a new instance. That's while that happens and is getting mining. You can see that there's sort of two interesting places to look in this contract for potential vulnerabilities. The first is this contribute method, which says there's this require keyword came into Solidity after I think 0414. Previously, you would have just written an if conditional, but the problem with writing this sort of thing where you have like if and then throw is that when you use throw in Solidity, it reverts all of the changes, consumes all of the gas for that transaction, and puts a zero onto the stack. So it's very, very difficult to debug. Whereas using a require, what it will do is it will revert the transaction rather than throwing it. Reverting means that you return all of the gas that hasn't been used to that point to the user, so it's a better user experience, and it puts a 1 onto the stack, so it's much easier to debug. So like using require is now sort of standard practice. Again, if you go and read the Solidity docs, there's lots of stuff in there about it. Essentially, we just need to make sure that the value of the message, which is another global variable available in Solidity, is greater than 0.01 ETH, and then a bunch of stuff will happen. So the contributions mapping for the address of the person who sent that gets increased by the value that they sent. And if that contribution is greater than the contribution of the owner, then the owner becomes the person who sent the message. Remember that the contribution of the owner here is set to 1,000 Ether, which we clearly don't have. So that's there's nothing really there that we can do to get into the contracts. What's most interesting, I suppose, is this fallback function, right? So clearly, like the name of the tutorial is pointing us to it. The fallback function gets called when you send a transaction to the contract without specifying what function you want to call, or that has, generally it's made payable because this is how you send Ether to contracts. So if I send Ether to this contract without specifying a method on it, it will automatically call this fallback function. And this fallback function requires that the message value is greater than 0, and that the contributions of the message sender is greater than 0. So we'll need to update that mapping first. And then if we send another message that has a value greater than 0, we will become the owner, right? So this is clearly like the vulnerability in this contract. It's pretty easy to see, and all you need to know is that in order to call the fallback function, you just use send transaction, which is a method that's sort of globally available. So we've got our instance address. It's pretty simple here. All we need to do is await excuse me, the contracts. The first thing that we want to do, like I said, is update this contributions mapping, right, so that we can pass that second part of the conditional here. So if we contribute, and the way that we send like value when we call, so generally you'd sort of make a call like that and maybe pass in some parameters if there were. But with Ethereum, you can pass in an extra little JSON blob, and that you can add a whole lot of information in about like the gas price, the value, and the data associated with each call. So in this case, we're already interested in the value, and we want to make sure that it's greater than 0.01 ETH, right? So this is like a little bit of a subtlety. Everything in Ethereum, like all amounts, are passed in way, not ETH. So we need to sort of understand how much value we actually need to put into this, because it's being passed in way, not ETH. So we need to make sure that it's greater than 0.01. Let's just say 0.02. There's the way amounts, so we can grab that. I'll also drop that link. Let's put our value in there. It should ask us to sign a message because we're sending value along with this. Seems weird. Okay. We should be good with that transaction. But look, seems to have succeeded. So we should be okay. The way that we can check that is by looking at the mapping contributions. But let's just carry on because time is short here. So if we've now sort of updated that contributions mapping, the next thing that we want to be able to do is call this payable routes over here, the fallback function. So we're obviously not going to call a method on the transaction, but there's the send transaction, which is globally available in Ethereum. And we need to make sure that, again, that the value is sort of greater than 0 there, right? So it doesn't have to be greater than the 0.001. Oh, guys, I've read that the wrong way around. So obviously, that's why it was throwing. Excuse me. We're going to need to call the contribute method again because it needs to be smaller than 0.001. Excuse me. So let's just do that again. Go 1 and take away a 0. There we go. That should not throw an error this time. That looks much better. Excuse me. So once that contributions mapping has been updated, we should be able to call the fallback function. Need to wait for it to be mined, which is always a bit of a bogus one to wait for, but this is the nature of the beast when developing on Ethereum. You can set up the next transaction while we wait for that. There we go. It's mined. So now we can send a transaction to the fallback function, and this one's value just needs to be greater than 0, right? So we don't need to give it a lot, just a little bit to register. It really doesn't matter. You can put in 100 or 10 there. So let's go and sign the transaction in MetaMask. Wait for it to get mined. So the reason that they're sort of going through this whole fallback thing is that, like I said, a lot of people include this payable fallback function in their contract so that the contract can receive Ether. But it's really, really, really important that you pay close attention to what you actually allow people to do in that fallback function, and especially like the order in which you go about writing things in that fallback function. So generally speaking, with Solidity, we have these two kind of rules of thumb that we work with, which is the first is like fail early and fail fast, right? So always puts your require statements or your assert statements or like the conditionals that allow access to more sensitive state-changing operations in your function, always put those first so that it fails early and it fails fast. The other thing is always do like optimistic accounting, which is something that will come to in sort of re-entrancy, which is like rather sort of behave as if the transaction has already gone through by updating balances in a specific way so that you don't open yourself up to this notion of re-entrancy, which is how the DAO got hacked, and something that we'll come to in a little while. You can see that our transaction has gone through. So now if we look at the owner of the contracts, it should be us, right? 0x8fd, which it is, right? There's our address. So we can be pretty sure that we've managed to take ownership of this contract, and now sort of all we need to do, right, is withdraw. So you can see this one, it's going to transfer literally the balance of this contract to the owner. Seeing as we're the owner, we're sort of more than happy to call it. So let's await the contracts. Draw. We don't need to pass anything to that. We will need to sign a transaction because obviously the transfer over here is a state-changing transaction again, so there is a gas cost associated with this. And while this one mines, and before we submit it, like it's worth just going into like a little bit more detail about gas and what it actually is. So that's actually been mined very fast. Like gas is the way, I suppose, in which Ethereum overcomes some security concerns around allowing a Turing-complete language to run on the blockchain. So essentially what we do is, instead of having like a 1 megabytes, like a data size limit, like Bitcoin does, we have this gas limit per block that is actually sort of dynamically decided upon by miners. So currently that gas limit is sitting like somewhere just above 7 million. And that's like, gas is literally just an arbitrary measure that you pay per computational cycle of the EVM, the Ethereum virtual machine. So like each computational step costs a certain amount of gas, and then gas costs a certain amount of ether, right? Which is how we sort of tie this mechanism for achieving deterministic computation, i.e. you can't have more computation done per block than is defined by the gas limits, to the notion of like crypto economics, right? So there's this cost if you want to submit a whole bunch of spam transactions and try and like DDoS or Sybil the network. There's this actual economic cost in addition to making sure that we can still have deterministic computation with a Turing complete language, which is pretty neat when you really think about it. And I'm more than willing to explain like a little bit more, because I know that some people, especially the developers, like get a little bit lost when we talk about gas. But as long as you remember, it's like there's a gas limit per block, which limits how much computation can get done, and that's like gas is just an arbitrary unit used to measure like each computational step that is then linked by the yellow paper to a price in ether. Then you'll be fine. So this transaction, I haven't signed it. Went off about gas without signing it. Excuse me. There you go. We should get that mined and get through in the next one. I'm not sure that we'll have enough time to go through all of these, but I will do as many as we can. You can see we've passed the level. That's super exciting. I really love this console art done by the Zeppelin guys as well. If you ever watch this, you guys really rock. This is awesome. So we can move on to the next level, which is called Fallout, which is like a pretty silly contract, but let's go through it. If we just get the new instance while I in there. Cool. So you can see again we're importing ownable. This time what we're trying to do is claim ownership of the contract again, right? So it's there's clearly something else that's wrong with this contract. You can see that we don't have nearly the same setup as last time, right? There's no sort of obvious fallback function to attack. There's no obvious in fact, to this contract, right? If you take a look through it, you can kind of satisfy yourself. There we go. That's been deployed. You can satisfy yourself, in fact, that it's very, very difficult, in fact, impossible at first glance to manipulate any part of this contract in order to claim ownership, right? If you look at the constructor as it's labeled, it sets the owner to whoever sends the messenger. to whoever sends the message, and then allocates, which is a mapping of an address to some unsigned integer, allocates that address, whatever the value was that went along with this contract deploy. But this is just to sort of highlight how people might say, sort of like, oh, look, our code is open source and you can take a look at it, but they can be kind of misleading. Because you really have to sometimes read very carefully smart contracts in order to understand exactly what they're doing. And if you look here, like this contract is called Fallout. And if you actually take a look like closely at what's been labeled as the constructor, it's actually FAL1OUT, which, like I say, it's annoying, but like it's really, really important to realize that something as simple as that can change entirely the behavior of a smart contract, right? So this, because it's a different name, is not actually the constructor and will not be called when the contract is deployed, right? It can be called by anyone. You can see that like in Solidity, and I suppose this is the other important thing that I should have mentioned earlier, is you have all of these scope declarations that you need to make. One of the things to be super aware of when you're writing smart contracts and working in Solidity is that functions and variables default to public, which is obviously like a hotly debated pattern, and there's been ongoing debate for like years about exactly why that is the case and whether it would be better to default to private, which a lot of people do feel is the case, but it's stayed this way for now. So this function is public, right, which means that anybody can call it. Again, if you sort of refer to that cheat sheets on Solidity that I'll send out, the sort of scope declarations that you can call are public, which means anybody can call it; external, which means only people outside, only like contracts and people external to that contract can call it. Then you get private, which is only people within the inheritance graph of this contract, right? So if you have like Fallout is ownable, then Fallout can still call private methods in ownable, whereas internal, which is the next one down, like means that only functions in this contract can call it. So yeah, like sort of external, public, private, internal. And then there's a few others like pure and constant and view and payable, but they all sort of relate to specific instances. So yeah, like this not actually being the constructor means that the contract will behave in a radically different way from how it looks it will behave, and all we actually need to do is call that method, and we'll be made owner of the contract, right? Because whoever sends a message to that function gets made the owner. And we probably need to pass some value in, just to sort of satisfy that constraint. So if we do that, should be able to sign it in MetaMask. Once that's signed, we expect ourselves to become owner of this contract, right? So this is like a bit of an annoying one, like I say, but it's really, really important to sort of like really drum it into people that even though the code is open source, you have to be careful when you read this stuff. And it's obviously like it's the sort of thing that auditors would go looking for in dodgy ICOs and that sort of stuff. So let's just take a look at the owner. We expect it to be ourselves, which it is. Fantastic. So we can submit this instance. So we should be good to go there. Let's wait for the pretty Zeppelin art to come through our terminal. There we go. So before we move on to the token contract, are there any questions about the last two and about this notion of a fallback function, or about like scope variables, how you declare those in Solidity, how you keep them safe? No? Is everyone still there?
I'm still here.
Awesome. Okay, so
Yeah.
the next level you can see You can see us sort of moving up through Rick and Morty, which I really, really dig. So we start off as Jerry and then Squanchy, and we're now sort of finally on Morty, which is super exciting. This is my level in Slack, so I'm always a fan. The goal of this level, you can see, is to hack the basic token contract below. We're giving 20 tokens, and we want to try and get like a very large amount of tokens, right? And the clue here is what is an odometer, which I found pretty obscure the first time that I looked at this, I must admit. And let's just get a new instance. So, like we've seen, some of the very basic ways in which Solidity gets manipulated, and the most basic ones are literally the fallback function, which often gets abused, and this notion of sort of trying to maliciously obscure code and mislead people about what is actually going on in your smart contracts. But now we actually get into some of the less nice features of the language, I suppose, which is really, really great for our developers to have a look at as you think about, sort of potential crypto-economic solutions within Status. So this, we should
So,
instances.
maybe also there is another security vulnerability that is not, maybe it's not mentioned there, but are race conditions. When you send transactions, you don't actually can be assured that your transaction is going to get minted or when it's going to be. And also there is another characteristic that the transaction, when you send it to the network, everything you send is public then. So there is some cases in some transactions, like for example, if you're revealing a secret for, don't know, a deed, don't know, many contracts can use secrets. So this, when you reveal the secret, everyone can see it. And then the secret could be front-runned by a transaction that pays more gas, for example.
Yeah, this is a very good point to make, particularly as we wait an unusually long time for one of our transactions to be mined, which it finally has been. But Ricardo is exactly right. One of the key problems, for instance, like the best way of describing this is like one of the key problems for decentralized exchanges operating on Ethereum is that there's sort of two opportunities to front run trades, right? Like Ricardo says, when you submit a trade, even in a supposedly secret format, people can look at that transaction broadcast on this public network and get information out of it that might allow them to front run the trade. And the other possibility is that the miners themselves are actually allowed to order the transactions in whatever order they like in the blocks that they find. So they often order it with transactions that pay higher gas costs above, so somebody can see your transaction and then submit in front of you, which is something that's both Ricardo and Richard will be able to go into good detail with, because it's something they actively try to guard against, and they have some really amazing work, particularly around secrets and recovery when it comes to identity and ENS. But that will be for a later tutorial, hopefully actually taught by them. So what we want to do here, right, it's a very, very basic token contract. And we can see that essentially there's a constructor that gets called and sets the balances mapping for whoever sent that message to the total supply, which is just the initial supply. So whoever deploys this contract gets whatever they pass in as the initial supply when deploying. And then there's just two other routes, right? Balance of, which simply returns that mapping, so there's nothing really interesting for us to look at here. And then this transfer function. So we know that there must be something like a little bit weird about this transfer function if we're going to be able to sort of manipulate it in some way to get more than 20 tokens, which have been assigned to us. We can find that if we sort of just await... Oh, in fact, sorry, contracts, balance of our address. See, that's broad. You can see that our address is, our balance that is associated with our address in that mapping is 20, as we expect. So we want to make that, and the big clue here for this tutorial is you want to make it much bigger, right? Preferably a very large amount of tokens. And that's a big clue, like in terms of also like the odometer, like how do we actually manipulate this to get ourselves a much higher number of tokens than we currently have, right? You can see that while this required statement looks fairly innocuous at first, right? Just require that like the balance of the message sender who's ever trying to send this stuff, like less the value that they're trying to send is always positive, right? That's what they're essentially saying there. But the problem with this, right, is that we've declared value as an unsigned integer, and we've declared balances as an unsigned integer. And so, like, that statement is always true. And what we can do is we can actually cause an integer underflow by sort of calling this transfer function with any address and a value that is greater than 20. Right, because that will cause an integer underflow in this require, which will assign to us an absolutely massive value in tokens, right? Which kind of leads me to like a little bit of a philosophical point about what tokens are, which is pretty interesting, I suppose. Like tokens are always just these mapping in smart contracts, right? So often when I talk to regulators. And they talk about like regulating Bitcoin as it applies to foreign exchange and moving Bitcoin offshore. And so that's just fundamentally the wrong way to think about it, because like the Bitcoin is already everywhere, right? It's these balances in a ledger, and all you're actually doing is signing over the right to spend an unspent transaction to somebody else. And in much the same way in Ethereum, what we're looking at here is tokens are just these mappings of addresses to unsigned integers that represent the balances associated with those addressings in a smart contract. And obviously, like the smart contract exists everywhere, but it's just like an interesting philosophical point to consider. This is actually what tokens are, and if you write your smart contract in this way, which seems secure at first, you can cause like an integer underflow, which will assign me like an absolutely massive number of tokens, right? I can sort of get like 2 to the 256 minus 1 kind of thing here. So if I await this contract, I want to call the transfer function. So like I said, it doesn't really matter who I transfer it to. I'm just going to transfer it to the 0 address, right? And I'm going to try and transfer 21 tokens because I know that I have 20. And this should ask me to sign a transaction in MetaMask, which I will do. And that will be mined hopefully soon. So the reason that this is included is like integer underflows are very, very bad in Solidity, right? They happen all the time in JavaScript, obviously, but like there's no sort of money associated with them, whereas there is here potentially. So you really need to watch out for them. The way that you generally watch out for them is, and the reason I suppose that the Zeppelin guys have included this in their tutorial, is that they've written a contract called Safe Math, which allows you, instead of doing this kind of like addition in smart contracts, you've got like safe add or subtract or multiply functions that you can call, and that will do it in a safe manner for you and make sure that this sort of feature doesn't happen, right? So the transaction's gone through. If I try and look at the contract, I mean the balance of my account now, right, you can see that if I go into that, there's this absolutely huge beast of a number. Right, it's to the 77 as opposed to 20 before. So I've gone and caused an integer underflow in this balances mapping and got myself a massive amount of tokens, so I can submit the instance and off we go. Hopefully, see some more awesome Zeppelin art in my developer console. This is the most pretty that my developer console has ever looked, I must admit. So. That always makes me happy. There we go. The next part, this sort of is called Delegation. You can see it's the Show Me What You Got head from Rick and Morty. Kind of a cool episode. And this really has to do with what happened to the Parity multisig wallet, which is still an ongoing debate and has caused a lot of people to seriously rethink how we handle governance on Ethereum. And on that note, I seriously suggest that you join the Ethereum Magicians group that I put in the channel yesterday, and also take a look at that document on rough consensus as it's been adopted in the IETF. it's just like it's a really, really great way of thinking about governance. It's not directly related to what we're talking about here, but it's really, really important for the ecosystem. And the more people that we have there actively debating this stuff in a constructive manner, which I know everybody at Status is capable of doing, then the better for everybody in general. And that's obviously like our goal at Status, right, is to be this crystal clear window into Ethereum and to improve the ecosystem first always. So the problem here is this low-level delegate call, which you can find again in Solidity, sort of read the docs, right? If you go and take a look through there, and how it can be used to delegate operations to these on-chain libraries, right? Which is what resulted in that famous GitHub comment, like, oops, I accidentally killed it, which referred to the parity multisig, which had millions and millions locked up in it, and is, like I say, still a bone of contention about how exactly or if they're going to recover those funds. So here is like the very basic contract. You've got delegates, right? It has an owner, which gets set in its constructor, and then it's got this function called pawn, which sets the owner to whoever manages to call that. And then here's the delegation contracts. It declares its delegate objects, and then it has this fallback function, right? It's not necessarily payable, but the fallback function calls delegate call, passes it the message data, and that will sort of like delegate the call onto delegates, which is this contract here. And if you pass in the right message data, you can call this function, right? You just have to know what the data signature of this pawn function is, right? And then it will call it using this, which operates in
actually, this sorry, Andy, this bug is actually about the first parity bug, I guess, because there was two parity bugs from this delegation. One was about you taking out ownership of any multi-sig wallet, because the initialization function was like open to anyone, and the other was about this killing the library.
Yes, sorry, you're absolutely right. And this was the first one. So this was when anybody could take control of the parity multi-sigs, which was kind of worse. but yeah, clearly those multi-sig wallets were not well written, and we highly recommend like the Gnosis ones. They're much, much better and have been audited. So this is how we can sort of take control of it. We need to figure out what the actual function signature for pawn is. And I suppose this is why this is part of the tutorial, because it's just something I suppose that you need to know about how we actually compose function calls on Ethereum at like in the bytecode itself. In order to pass through the right message data to make this call here, what we need is the first 4 bytes of the KEKAK 256 signature of the 256 hash of the function signature. So let me say that again. The first 4 bytes of the KEKAK 256 hash of the function signature, right? And then we add 0x in front of that. So if you put in your function signature, whatever it is, in this it happens to be pawn, but like if you had parameters, you would pass in their types, right? So here, like our function signature is very simple. It's just pawn, and the first 4 bytes is the first 8 characters, which goes to there, I believe. So that's what we need, plus a 0x. And what we want to do is we want to sort of await this contract call again, as we've been doing. And we're just going to send it a transaction here, right? Because we want to call this fallback function. So there's no need to call like any of the roots on it, right? Let me see if I can spell that right. Then transaction. We don't want value this time. What we want is data. And there's lots to be said about like this notion of data, right? Like I say, you need to actually add a 0x in front of it in order to call the function signature. Again, like there's this wonderful video from Gav from very early on in Ethereum, which like explains this notion of like everywhere there's data, there's network, and everywhere there's network, there's data. And this is again one of the most interesting things about these kind of networks. So you can see here that like making a call to a function is as easy as putting in like the data, and that like literally in the bytecode, this is how it gets composed with a 0x in front, and then the sort of first 4 bytes of the KEKAK 256 hash, and then you append onto that padded to 256 bits all of the sort of parameters that you're passing in. Again, like Jacques Wagner is probably the best person in the organization to ask about this kind of stuff. And if you ever need to read opcodes and stuff, he's the man to approach. So if I send this transaction, we should be able to, okay, that's didn't like it. Oh, I need to actually, sorry, excuse me, get a new instance before I try and do any of this stuff. Should always just make video demos beforehand, but now we'll have to wait for this contract to be mined. So yeah, Jacques is really your man to talk to about sort of trying to read contracts, like low-level contract details and what actually happens when it gets compiled down to bytecode. You can always come and take a look here in the Solidity browser, which is somewhere that we're going to come next. If you want like a much clearer picture of what's actually happening, like as these Solidity contracts get compiled down and deployed onto the network. For some of the next tutorials, we're actually going to need to write like our own contracts. As you can see here, I've sort of got some of them prepared. So this is a great place to come, and then if you, I'll show you now. I suppose exactly what's going on there. We should have this be mine. There we go. And we should be able to send that same transaction. Find it in MetaMask. And wait for it to be mined. The other cool place where you can go if you want to see like low-level contract details and the actual like opcodes, especially of live calls, it's what we use a lot for status open bounty, is on etherscan.io itself. If you pass in sort of remix as a get query, then you can actually get to the same sort of debugging and stack tracing like that is available over here. That there's a debugger, and you can do like a full stack trace whenever you deploy a contract and stuff. And this same thing is available on Etherscan itself and can help you sort of try and debug any live transactions that you might have been struggling with. We should be good there. The transaction has been sent through. So if we look at the contract owner, let's see if we have managed to take. We have, great. So we can submit this instance again and move on. To force, which is a pretty neat one because we start writing our own contracts. Obviously, not before we get another great shower from Zeppelin in the console here. So I've literally got 2 minutes left, and I do very, very briefly want to show you this this remix browser, because this is actually where you're sort of going to come. Those will come back to that. Yeah, this is where you're going to come to write your own smart contracts. So this is basically like a browser-based IDE for Solidity. I'm just going to do this over there. And you can come here. Like, it's very, very easy to write your own smart contracts, iterate through very, very quickly, and see like what works, what doesn't. You can obviously like compile each thing as you go through. So when we are sort of well, at least when I'm writing smart contracts, this is where I'll come to test stuff. And then I'll obviously, like, once I'm happy that they're compiling properly, that they're doing the things that I expect them to be doing and behaving in the ways that I'm expecting, then I can actually put them into like my Embark project and work on the actual sort of like web app parts of things as you go through there. There's a whole bunch of like various settings and stuff that we want to go through. But here we go. We're getting well done from our Ethernaut tutorial. I think I was spacing my screen here. And this is the last level that I'll be able to show you. Sometimes you can like force people's contracts to do things that they don't want to do. So like they've literally written this like contract which has absolutely nothing in it. Just a cat saying meow in comments, which is pretty neat. The thing that they want to highlight here is that like you need to think about like all of these weird things that are, like apply to computing on an open, transparent, publicly accessible like surface like Ethereum, right? There's 3 different ways in which you can actually send Ether to a contract, even if it doesn't have a fallback function that is payable. You can self-destruct your own contracts, and if there's any value associated with it, like you can specify the address that gets sent to, which is exactly what I'm doing here. And I would pass in the address of my instance into this self-destruct function, and it would send send value across to like this specific instance here. You can specify an address as the reward mining destination. So if you mine a block and you get a reward for it, you can specify an address and send ether to it, and it will sort of automatically receive it. And you can send ether to a contract before its creation, which is a slightly more complicated process that I don't really want to go into. But it's just, again, like, it's important. That ties into what we were talking about in terms of the fallback functions, right? Is that, like, even if you think, like, if you have a route in your contract that you think no one would be able to ever call because you can't send ether, or like there's some kind of logic that you're sort of relying on that is external to your contract, it can be a very, very dangerous pattern for developing smart contracts, because there are these like sort of caveats about, for instance, the fact that the reward mining address destination can be set, and like contracts can self-destruct and send ether to certain places. So if the security of your contract depends on that, then that's obviously not a great thing. I don't have the time to like go fully into like the rest of the stuff, but it's really well worth it. If you want to chat to me afterwards about how to do the rest of these things, or get links to other folks who have written about going through them, then please do. Thanks so much for taking the time to listen through all of this, and like hopefully it was useful to you guys. And please just put all your feedback in the Study Fundamentals channel, and then we can use that to actually put together some really useful development resources for Status specifically as we get out into our closed beta and onto the main network, and all the exciting things that are coming in the next few months. So yeah, thanks again, and I guess I'll see you next time.